Okay, our next speaker is Marc Truter, also from Institute from the World of Geometry. I've not seen very SPAAM, but he is using machine learning to do some nice work on building a periodic table of shapes.
Thank you. Yeah, so yeah, I do algebraic geometry, nothing to do with SPAAM. But I recently got into some AI stuff like everyone else this year. And I'll be talking about how I essentially have been using it in my project. And I think I'll basically spend the first 10 minutes just kind of describing my problem and explain algebraic geometry by pictures. And then I'll try and explain kind of some of the machine learning stuff, the algorithm I have, and show some more pictures as well. So if you don't get anything, hopefully you can look at a bunch of pretty pictures and feel like you got something. Okay, cool. So the goal of my PhD is to kind of build this periodic table of fundamental shapes in algebraic geometry. I'll kind of give a rough idea of what that means, kind of as the talk goes on. But basically, there's a finite number of them, and I want to find all of them. I'll explain also how they're fundamental. And one kind of obstruction to finding these is that the space we have to search in is really vast, is really big, and determining some of the important properties is really expensive to do. Which basically makes it a bit of a nightmare. And so this is kind of where AI comes in, kind of like the solution to most problems this year is supposedly AI. But anyway, yeah. But this is more kind of classical AI stuff. And I'll be talking about kind of a deep reinforcement learning algorithm I made for it. Cool. So what are these shapes? So in algebraic geometry, we study these objects called algebraic varieties. And they're basically the shapes which are the solutions to polynomial equations. And because they're solutions to polynomial equations, they kind of come up throughout science and maths. So like a very popular one is the elliptic curves. So this is like the core object of study in number theory and using cryptography and stuff. There's also some kind of more niche applications like in phylogenetics. And also we'll see an example of kind of subclass of varieties that are kind of the core objects of string theory as well. Okay, cool. And I'll also explain what this notation means. That's going to be quite important. But the point is that we can draw this picture and we can see it and it's shape. Okay, cool. So if we look at that example, how did I draw that shape and what does that notation mean? So donate my varieties in the following. So x6, that means an degree 6. And in this space, so before I start that, you guys might be more familiar with some varieties that you kind of see in school. For example, it's x squared equals 0, and that can live. This is just the quadratic equation. Algebraic geometry, we kind of upgrade from r squared to complex numbers, because things work so there. And you can even encode them in this thing called projective space. And in this projective space, make things even nicer by giving some of our variables weights. So it's a different way to encode it. You can also write elliptic curves in terms of this, but you can also write in terms of this projective space notation. So give x equation 6. Good. X, Y, Z is 1 plus 2, 6. So even though we do algebraic geometry, it's all very combinatorial because we kind of work with problems like this. Cool. Does anyone have any questions quickly about this? Okay. And the solution to this equation is what I drew here. Okay, so another important property I want you to know about these shapes is that they can have singularities. So I'm not sure how clear it is on the slide. It is like we'll scrunch a bit. And this is kind of one of the first examples I have for my PhD. A new example with the singularity that is very, very nice to work with. Yeah. Okay. And the previous example was smooth, and which makes it much nicer. Cool. So why these objects are fundamental. So without run it through this black used to Fano collab out or my PhD. The Fano. The elliptic curves are an example. And general. So if we saw before it, so for the elliptic curve, we had x6 in P1, 2, 3. So alpha here is just 6 minus 1 minus 2 minus 3, which is 0. That was just that the elliptic curves are a club. In a similar way, if we worked out the alpha for this one, we get minus 1, which tells us it's a Fano. Cool. Any questions? Okay. So in particular, when we kind of reduce to these 3 atomic pieces, they have this extra property. So if they do have a singularity, that singularity has to have this property called terminality, which is basically my whole PhD. So yeah, terminality. So this thing called terminal, we're going to talk about this a lot. So basically, when we have our shapes, we want to check if they have a terminal singularity. And not all singularities are terminal, but everything you can reduce in this world before will have, at worst, terminal singularities. So we know it's in that world if it has a singularity like that, and if it doesn't, then it's not in that world. Okay. And basically, so kind of one of the rules for my PhD is coming up with this test to determine if one of these really nice singularities is terminal. And that's where a lot of the computational cost comes in, because checking this is like pretty difficult to do. Okay, cool. So in 2016, this guy called Bakar, who ended up winning the field medal for this work, proved that there are only finitely many Fano varieties with these singularities if you fix the dimension. So, for example, here we're in dimension 1. So dimension 1 just means and all of the Fano varieties dimension 1, we know them. 2, so that's surfaces, we know those. This is good. Dimension 2, it's good. There's some partial results there, and that's kind of what most of the work's been done in the last 50 years is all dimension 3 stuff. So those are called threefolds. But I'm essentially looking at dimension 4, where a lot of things are very much untouched, and things get even nastier, and the space is even bigger. And essentially, in my PhD, what I want to do is try and understand dimension 4-fold varieties. And in particular, in dimension 4, we have that our varieties will have this form XD, and they will have 6 weights. So why 6? Because if we have 6 weights here, that means that this space we live in is 5-dimensional, and we cut out the space by one equation, and so we're left with 4 because that's 5-dimensional. Cool. Any questions? Okay. So that gets me onto essentially how I encode this to be able to do some machine learning stuff on it. Okay, there's a few different ways we can encode the data. So initially we can look at it, right? We have a D, we have a bunch of weights. We can just encode it as like an integer vector, D, A1 up to AN. But we can actually like reduce the dimension further. And if we want to stick with Fanos, because why do we want to stick with Fanos? Because we know there's finitely many, so you can build a periodic table of them. We can actually fix our alpha value. So before, our alpha value, which is our degree, if that is less than 0, it means that we're in our Fano world. So this is this slide back here. So yeah, we get a Fano if our alpha is less than 0. So maybe let's try and fix our alpha to force it to be Fano. So if we fix our Fano, our alpha, sorry, that's 0, right? We're going to get a Fano. But if we fix it to be -1, then we can rewrite it as d equals -1 plus the sum of ai. So if we know all our weights, then our degree is determined already. So that basically means if we fix our alpha beforehand, then our d is determined by our weights only. And that means that we can encode the data one dimension lower just by our weights. Any questions about this? Okay. And the point is that, so now we have these like varieties, very complicated objects, and we've encoded them basically in this grid world of integers. So how does AI fit into this? So let me draw the picture. So let me draw in. I'm actually working in 60, which makes everything harder. Point, for example, represents the point 1, 1, 1, okay, 1, 1. So 6 of them. And that, before you remember, corresponds to x in p, okay, and then 6 of those ones. And because we fixed that alpha to be -1, that implies d is -1 plus these, which gives us 5. So this point here corresponds to 0. And similarly, we can pick any point here, and it will correspond to a variety. And kind of in this world of reinforcement learning, we want to put our rhythm with something. So what was our goal? So let's say our goal is to find as many of these examples as possible where the point is terminal. So in this case, actually, this example is through my algorithm. Thing has singularities. And so good. But the point over here, the algorithm might run and say, okay, this thing doesn't have terminal singularities, so we don't care about it. We want to throw it away. And in fact, in the terminal. And from on, I'm going to call kind of terminal points. They're going to be synonymous. So, and then if it's not terminal, it's going to be a non-reward. So basically, I have this space, little breadcrumbs, and I'm going to get my agent to try and find as many of these breadcrumbs as possible. So there'll be some over here. Okay. Any questions? Okay. So what do I have to benefit me in finding these? So I think in the next slide, I'll kind of go on to all the challenges because there's a lot of them. But the kind of one bit I can use is that these raw points, you can see them in black here, I kind of, in the global sense, kind of clustered together. So this is a partial classification and Al, who has Warwick. Classification for very, very fraction of the total periodic table, so it's just a small corner of it. But they did find all of the ones in that corner. And that helps them find all of them. First one, plane, I've just projected that all on, projected it all onto the second and third coordinates, projection into different sides, so you kind of get an idea of the dimensional picture. Okay. Cool. So the challenges. The rewards are really, really sparse. So in this picture, it may not seem like that because I've kind of compressed them and put them all on top of each other. They will look very close together. In reality, in 6-dimensional space, they will kind of spread apart. And the search space is the part in gray. So you notice I'm only looking at half it because I've removed another half to reduce symmetry, or to remove symmetry, sorry, because we can order the numbers in different ways. So that just forces the numbers to be ordered sequentially. And another issue is that you can only evaluate them locally. So what I mean by that, so essentially, I don't know where all of the other reward points are, and I have to search the point to check it, which means it's very computationally expensive. So I check as I search. For example, okay, that makes a lot of things easier. Machine learning, if you know where everything is already, you can just use a neural network and then kind of predict where the rest are. Neural networks are particularly bad at kind of searching outside of where they're used to, which is a big challenge. And they're expensive to determine, so I said that before, to check this terminality condition. And it's also in kind of this non-informative environment. So a lot of the times with machine learning, for example, these reward points, you can imagine a different problem, right? Where you have a car. So imagine you're trying to this car has some vision. With that vision, it can kind of look ahead and it can see, oh, I'm about to crash into something. In this case, my AI agent kind of can basically get no information at all about where it is. Being put a reward point doesn't tell you that there's a reward point right next to it, so it's kind of hard to read. And the only positive I have is that they're spatially clustered. So that's kind of what I base all my algorithm on. Cool. So how do I reward it with those breadcrumbs? So every time it finds a breadcrumb, I give it a sweet of 1 point. If it finds it, if it doesn't, then I tell it off based on how long it took to not find one of those breadcrumbs. And basically, you feed that back into your neural network, and that will kind of model where it should search. But this is kind of the really tricky bit, and this is where kind of a lot of the, I don't know, yeah, a lot of the time is spent, because if you give it too much reward, it'll just go off and explore and do whatever it wants. If you don't punish it enough, we'll also do that. If you punish it too much, it just won't look anywhere. So it's like really hard to kind of find this balance between reward and punishment, kind of the carrot and stick. And also you can like say if you want to search for certain types of points. So say if I want to find really exotic ones with really far away, then I can reward it for finding those by adding a little bit of reward in the reward function for finding like higher degree examples, bigger D examples. Cool. So BAM algorithm. I'm not going to go exactly everything in terms of, I'm not going to go through everything in the algorithm, but I just wanted to kind of give an idea of what like the reinforcement learning architecture looks like. So this is kind of one, there's lots of ways I think it can be improved. So how do I search, right? So I've already said that. So in, I'm going to, is that I'm going to start with a point, start with this. So that's number one algorithm. 2, I'm going to find all the neighbors. So I'm going to add all of the, what color I use? Blue, that might be good. I'm going to so minus away from it, 1 away from it. Oh, yeah, of course, grow. Yeah, sorry. Is red, yellow maybe is best, right? And then when I look at all this, I'll check if they're all points, and I'll also add them to a search queue called queue. I check if they're points. If they are, reward based on and replay bar basically what at that point it did facing it every now and then, kind of feeding that back. So that's kind of, so this is like constantly updating it. Do not find. So for example, if just went off on some tangent and then like explored. Cool. Any questions on this? Okay. Okay, final slide. So here's a picture. So this is the search algorithm in action. So does mean the dark blue points are where I found one of the small sub-classification, and found that are non-quasi-smooth, so not in this tiny subsection. The non-quasi-smooth basically is like everything else. which is the rest of the application. From these pictures, nearly all of them are quasi-smooth. But the point as well is that it's all projected onto each other. So the non-quasi-smooth ones make up like 60. But they're not. It was done in like 50 minutes. For comparison to the previous like using that algorithm would just that's basically much.
Thank you, Mark. Any questions?
Yes.
This conjecture you mentioned that is breadcrumbs are clustering. We have it's that these varieties are clustering, right?
Yeah.
How strongly do you believe this is actually true?
Okay. So I guess this is just from observation. So I have no kind of mathematical proof. This is kind of looking at the from before. But in a sense, so obviously I started before having this terminology. If that criterion is if you're very kind of okay, one thing you can notice, for example, you can't this ridge. Sorry, it works. It's very combinatorial, and you can imagine if you're close to that point, then you're very close to satisfying the same condition. That then close to a point that is terminal means you're more likely to be terminal.
It's not actually based on the conjecture, is it?
It's not, no.
Oh.
No. So the clustering is just something I observed. I was like, this is a good way to search the space. Yeah, but I mean, if you then think about it retrospectively, the criterion, I guess, like backs up that, okay, these things should be roughly clustered. Yeah. Yes.
Like does genus only correspond to this alpha that I do it? Or
No, it's a good question. So for example, you could have so yes, actually, someone called Tamarai gave a talk, and she basically has her own classification, one dimension lower. And so she has a bunch of examples where they have varying genus. Oh, no, right, actually, it does. So there's for the genus based on this. Yeah, I think it should be. Yeah. Yep.
choose. I guess like for your just one.
Yeah.
Punishment. Could you go back?
Yeah, of course, yeah. Yep.
Is there any particular why you chose us like?
So of course, so I had on. I used 10 now. And it's kind of these things. Anything, and don't reward them. So, for example, if I gave it a high reward of 10, then it would be over. Basically, yeah. Why have I chosen one? Sorry, I've chosen the punishments for that. Just by of what works. So, I mean, there's a lot of like common ones. So, for example, a function would be 1 and 0. But I tried that. And then I did that, but then it was a bit too strong. And there's a lot of other, I think, spend a lot of time kind of bumping it up, bumping it down, then changing another hyperparameter. And when the one needs to change, I think it's just the ratio together. And unfortunately, in machine learning, it's really hard to understand why certain combinations work better. In retrospect, it's because a lot of it is just, yeah, you kind of just let it.